Okay, and so here's where we are now. We'll start with this language models overview, and then we'll take a short break, maybe a 5-minute break, uh, once we're done with the overview, and then we'll move on to actually seeing these things running in code. Okay, so we hear a lot about large language models right now. I mean, all of the hype about um, things like ChatGPT and Claude and so on. These are large language models. A language model is a more general concept. Language models have been around for a long time, well before the current craze on large language models. We kind of want to take a step back and say, okay, well, what exactly is a language model? When researchers have been building statistical language models in the past, specifically what's the problem they're trying to solve, and why is that challenging? Um, Once we have an idea of what a language model is, we'll get a sense of how language models are used to generate text, right? Because ultimately, the way you interact with these models, we've seen chat models where you ask the model questions or you give the model requests and then it generates text in response. We'll see exactly what, in the context of language modeling, that generative process looks like. And then hopefully get some appreciation for why building accurate language models is difficult. Like I said, language models have been around for a long time, and people have been working on language models for different applications for decades. But kind of this recent excitement and these recent leaps that we've been seeing, um, that have been enabled by large language models are precisely because some of the harder problems associated with language modeling have been nicely solved by the latest generation of models. So we'll get a sense of why did it take so long to get here? What were the challenges that individuals developing language models have faced in the past? And so for people who've been who are up to speed on language models and they've heard of things like transformers, um, that's often a starting point when you're talking about large language models. There's the transformer model architecture, and that's something that we're not going to cover today. There are other, like I said, there are other classes that are later on in this course that are devoted entirely into diving deep on that. Here again, we're just kind of painting the broad picture. We're not going to dive into the details of the transformer architecture, other than to briefly mention it and mention, how it helps address some of these things that make language modeling particularly challenging. Okay, so what is a language model? Yeah, so language models are the models that are at the heart of applications like ChatGPT. And what a language model is, it is a statistical model that can be used to generate text, right? These are basically models that are exposed to lots of written text and learn from that exposure to written text. They learn statistical relationships between sequences of words in typical word sequences. So once you have a model that understands these statistical relationships between um, the individual words that appear in a sequence of words, you can then sample from that statistical model to generate text. And that's the process that models like ChatGPT use when they actually generate the outputs that they provide. So one of the basic ideas in language modeling is to cast the problem as generating a sequence of tokens. If I'm going to generate text, um, that's typically cast in what's called generating what are called tokens. So the idea of a token is that when you build a language model, you typically have some predefined vocabulary, right? So it could be a vocabulary of words, for example. You could say, okay, I've got this language model. That language model is going to work over the space of, say, 30,000 different distinct words. And it's never going to veer outside of that, right? We're never going to look at words outside of that. Everything that it learns and everything it knows um, is going to, work on sequences involving only those words. Now, typically, the way those individual pieces of the sequence are generated is they could be words, but they could also be parts of words, or they could be individual letters. So the idea is that if I have a string of text, I might be able to break that down into individual words if those words are in my vocabulary. If I come across some word that isn't in my vocabulary, then I can at least break that word up into a sequence of letters, right? If I have the alphabet in my vocabulary. And so that's typically what a modern tokenizer looks like, is it's basically the vocabulary of your language model, but it contains things like words, parts of words, like things like suffixes and prefixes, as well as individual letters. And when you have a tokenizer, or you have a definition of your tokens in your model, typically the idea is that tokens are, these are the individual entities in your vocabulary. They're going to be represented by unique IDs, right? So if I have 30,000 tokens in my vocabulary, I've got token 1, token 2, token 3. And when I take, a given sequence of words and I convert that into a sequence of tokens, basically I convert it into the sequence of the individual IDs. And again, those IDs might correspond to individual words or parts of words. And so this graphic kind of says it all. So this is a sentence that a language model might process. It has, "Do it is a great company to work for." And "do it," must be the name of some company. And it's spelled capital D, small o, small I, capital T, "is a great company to work for." And then it has a period at the end. And so the idea is that a language model, first of all, if it's going to process a sentence like this, it needs to break it up into a sequence of tokens. Now, things like "is a great company," those are all common words, right? And so those common words might be words that are in my vocabulary. But something like "do it," spelled capital D, small o, lowercase I, capital T, is this proper name of this company. That's probably not in my vocabulary. But my tokenizer should be able to break a name like that up into individual components that are still parts of my vocabulary, even if they're individual letters, right? And so the idea here is that down here we see the tokenized version of this sentence. And so the important thing to notice here is the way we've broken up the name of this company, "Do it," is we have the word "do," capital D-O, that maybe that's a token that's in our vocabulary. Then we have the letter I that's in our vocabulary. Then we have the letter capital T that's in our vocabulary. So those are the first 3 tokens in the sequence. And then all the other words, because they're common enough words, are also in our vocabulary. We have "is a great company to work for." And then the period is also, so the punctuation is also going to be part of our vocabulary. And each of these individual tokens has a unique ID in our vocabulary. And so 5211 is "do," capital D-O, 72 is the letter I, 51 is the letter capital T, and so on. And so basically you just have this sequence of unique IDs representing the sentence that I input into the model. So the reason why we're going through this is that it's important to just kind of simplify and step back and say, okay, now when I'm building one of these statistical language models, the fact that there's nothing really special about the fact that it's language. It's really just, it's a sequence of unique IDs, right? If I give you a sequence of unique IDs and there are some interesting patterns in those sequences of unique IDs, like certain IDs tend to occur near others. That's the things that these kinds of models are going to learn by being exposed to lots of text. And that's all that matters, right? The fact that it's language, or if it's English, or if it's Spanish, or if it's French, or another language, it doesn't matter, right? What matters is the sequence of unique objects, and there are some interesting patterns, or some repeated patterns that we can recognize when we build a model on it. Um, so there are a couple questions here. I can see if we can answer these ones quickly before we move on. So a language is usually associated with a grammar. Does it mean models have an idea of a grammar in the language which they are generating text? Not necessarily, right? So a grammar might be something that might be prior knowledge that we have about the language before we go about building a model. And you can build language models without having any prior knowledge of the structure other than the vocabulary, right? So if we know the vocabulary, we know how we want to assign words to unique IDs, then we can entirely rely on a statistical model to learn various relationships, right? Without necessarily saying, oh yeah, and by the way, those relationships need to satisfy these rules of a grammar, right? So typically when people build language models, they're not imposing any hard constraints from a grammar on top of it. They're purely learning those relationships statistically. And there's also a question about why not break do it into two separate words, do and it, since it is a common word? It's a great question, right? And so typically, if you look at, so I keep saying tokenizer. A tokenizer is the object that will convert a text string into a sequence of tokens, right? And so when you look at most tokenizers that have been built for um, most models, they treat capital and lowercase letters differently, right? Because if I want to then go back from my tokens to English text, then I want to render all the capitalization correctly, right? And so I might have a word in my vocabulary for do, capital DO. I might also have a word in my vocabulary for do, lowercase d o. And those are two separate tokens that I'd keep in my vocabulary. I might have Similarly, I might have a token for it, capital I, small t. I might have a token for lowercase I, lowercase t. I probably don't have a token for lowercase I, capital T, because that's not typically uh, the way the word it is formatted. I think that, that's why this example is interesting, right? Because we have this strange capitalization that illustrates that we can't rely on the word it with this specific capitalization being in our vocabulary. But we still have all lowercase letters and all uppercase letters, so we can always break this down into the sequence lowercase I, capital T. Okay, and so yeah, there's a question of why do we need tokens, right? So we need tokens because ultimately what we want to do is we basically um, want to build models that can recognize patterns in sequences of IDs, right? And you can say, okay, well, couldn't I just do that with words, right? Um, I could just say every time I see a certain word, I could basically split at white space and say that's a word. Maybe I could treat punctuation as an object. Now I'm already kind of getting at the idea of tokens, right? You say, okay, well, I need to represent more than just words. I need to represent punctuation. I need to represent individual words. Um, but then there are also situations where maybe you have compound words that aren't in your vocabulary and you don't see them very often, but you can extract something from, um, you know, the meaning of the individual parts that make up that compound word. So maybe it's helpful to split that into two parts that both have some meaning, right? And now we're not quite always just using words as the unique entities, but we're using parts of words. And now we're basically at the point where we're saying, yeah, that's what tokenization is, right? It's basically, sort of defining the finite vocabulary of a language model, which might be individual words, it might be punctuation, it might be parts of words, it might be individual letters. Um, and that's ultimately what we're trying to build sequences on. Yeah, and so another question about, does the space between letters and words, is that considered a token, or is it used to generate tokens, just like a split function used by strings? Yeah, so generally, um, you're not modeling white space as a token, right? Like you're not saying, is white space token a white space token, great white space token, right? So that space between words is not considered. So even if you have situations like do it, which is all one word, then those are three tokens that represent, part of the sequence. And then the next separate word is just the next token. Okay, so we're going to move on from this section and we'll come back to additional questions, either at the end of the module or as they come up in later sections. Okay, so what is it? What exactly now is a language model? Now that we have this concept of tokens, well, a language model is basically a conditional probability function over tokens. And so don't worry too much if you don't have a probability background. I'll try to explain this intuitively as well. If you do have a probability background, great, you can kind of map that onto what we're seeing here. But basically, what a language model is a probability model that says what, given the prior sequence of tokens. So if I saw, for example, do it is great, right? Where this is one token, this is a token, this is a token, and those were individual tokens, right? So I see some partial sequence. So this is a conditional probability function that says, given some partial sequence, right? So this Wn, W1 through Wn, suppose those represent these first tokens that we have written up here. What is the probability that each given token in your vocabulary is the next token in that sequence? So basically what we're using this model to answer is the question of, if I said, do it as a great blank, what do you think blank is? Right? So that's basically what this conditional probability function would give us. It would say, if I said, do it as a great blank, what do you think blank is? You might say, well, there's some probability that it's place, there's some probability that it's company. Then there are lots of words in my vocabulary that's probably very little chance that it's going to be. Like it's probably not giraffe, right? There are lots of words that are completely unlikely to be the next word. And so you could think of having some model that just assigns a probability to every single possible next word. And that's exactly what a language model is, right? So once I know that I have this, vocabulary, what I'm looking at are sequences of items in that vocabulary. I can then move on to the task that language models solve, and that's just basically predicting the next item in a sequence. And if you build an accurate language model for any given sequence that you can give it, and even if the sequence is pretty long, it can come up with reasonable probabilities, reasonable choices for what the next word is. So I'll give you another example. And so this given sequence that we're conditioning on, this is what's generally called the context that's provided to the model. So I provide a model with some context, which is maybe a partial sequence of tokens, and then it produces probabilities over what single next token it thinks comes next. So I give you another example. So suppose the context I use is, this morning I went to the, right? And so I'm going to tokenize this, meaning I'm going to take this string, I'm going to convert it into a sequence of tokens. I could pass that, if I had a language model, I could then pass that sequence of tokens to the language model. Those would be the ones I would condition on, playing the role of this W1 through Wn. And then my language model is going to give me probabilities for every possible next token in my vocabulary. So this is an example where I actually passed this to an actual language model. And then I took all of the next tokens and I sorted them in descending order of probability. So the first most probable token is office that had a probability of 0.031. So basically a 3% chance. The language said there's a 3% chance the next word in that sequence is office. Then there's also close to a 3% chance that the next word is store, but it's slightly less likely. There's a chance that the next word is local, right? Because maybe the sentence continues on, right? This morning I went to the local post office, right? So local is also a reasonable choice for the next word. Gym is also then the next choice that in terms of probability, 0.023. So you get the idea, right? This list could go on and on. If I had 30,000 tokens in my vocabulary, I could extend this list all the way down through all those 30,000 tokens. And very soon I'd hit a point where there are going to be lots and lots and lots of possibilities, possible next tokens that had extremely low probability. These are words that just wouldn't make any sense in that context, right? But for these first few choices that I've presented here, these all are very, these all intuitively seem like very reasonable um, next choices. And the thing that's kind of interesting about this is that, like I've been hinting at, is, you can build these language models by basically showing them lots and lots of text, and they kind of learn these statistical relationships, right? Given the words I've conditioned on, what's likely to come next, just by based on what it's been exposed to. But there's a lot of knowledge that's actually captured in here if you do it right. Like, knowing that gym is a reasonable next word. Well, yeah, because people often go to the gym in the morning, and sometimes it's the first thing they do. So you could, say that it seems like the model knows this, right? Really, it might have just picked up on that being a common statistical pattern, like it's seen sentences like that in the past. But maybe if your model is doing something clever, it's actually encoding some knowledge about the world, right? That it's being able to recall when it completes a sentence. Okay, so we've basically said that a language model is just a model for predicting the next word in a sequence given a context. And more specifically, it's rather than picking a single word, typically it's giving you a probability assigned to each possible next word in the sequence. So what about generating longer sequences of text beyond just the next word, right? Like, so I have this morning I went to the blank. What if I wanted to use that to, uh, as kind of the seed to start telling a long story, right? I wanted to tell a long story. This morning I went to the office, and when I got there, I noticed nobody else was there. Um, I pinged my manager, and they told me that today was actually a holiday, right? Like I wanted to actually generate a long sequence of text rather than just one word. How would I go about doing that? Well, this is basically an interesting idea that shows that if you have a model that can produce just the one next, can produce a reasonable guess for just the one next token, then you can just use that model over and over again to generate longer sequences. So the idea here is that let's suppose I started out with the context, the man is walking, and I plugged that into a language model, and the language model gave me a bunch of choices and probabilities assigned to those. And then I picked one of them, right? Maybe I picked the most probable next word out of all the possible next words it could be. And maybe the most probable next word is down, right? So the next probable next word is down. If I want to generate a longer sequence of text, all I have to do is take that most probable next word, stick it onto my context, and then pass the whole thing back to the model, where now my new context is the man is walking down, and say, okay, great, now what word comes next? Well, if I take the most probable next word from my language model, maybe it's the, I can take that, I could stick it back onto my context, and now I have the man is walking down the, and use my model again, and it predicts street. and then I stick that onto my context, and it predicts a period. It says, okay, that's about it. The sentence is probably over there, right? And so here, what I was able to do is I was able to start out with the man is walking, and I was able to generate the full sentence, the man is walking down the street, period. And so the idea here, the key takeaway is if you can predict just the next token, if you've got a good model for just predicting the next token, then you can use that model to generate a sequence. Every time you just pick a next token, you tag it onto your context, and you just pass that back into the model, and then you generate the next one. And so, here we said, okay, one way you could do that is you could just pick the most probable next token. It turns out in practice, there are different ways for selecting that next token. That's one reasonable way of approaching it, but there are other things that people look at as well. But the key takeaway here is that if you could build a model like this one we have here, right, where I can get a probability of next words in my vocabulary given a sequence, that's a really powerful thing, right? If you have a model that does that task really well, then you can use that model to generate text given an input. So there are a couple of quick questions that we have here that I want to get to. So one question is, what factors determine accuracy in conditional probability? So I guess I'm sort of interpreting that as, okay, so let's suppose you build this model. How do I know it's accurate, right? I can say the conditional probability is whatever I want. How do I know that it's accurate? Well, typically the way this is handled is that accuracy can be measured empirically, right? So often when people are building these kinds of models, they you basically you have text that you're training your model on. Like let's suppose I was training my model on the sequence that I have here, predicting the next token in a sequence. When I'm training my model, I might pass this in as a context. I might try to predict the next word, and then I could compare that to the actual next word. You can say, okay, if I was actually predicting the next token, and if I got it right, then my model's accurate. If I got it wrong, then it's not accurate. Well, we're not actually predicting exactly the next word. We're producing these probabilities, but you can have sort of more sophisticated measures of whether or not the actual next word was one that the model said was probable, or is it one that the model said was improbable? If the next word is often one that the model said is probable, then the model's doing well and it's accurate. If you're all the time finding that the next word is something that your model is saying is improbable, then your model's probably not doing a very good job at modeling this probability. So it's a good question. It's exactly what we're measuring when we train these kinds of models on data. And it's the task that we're ultimately training these models for is to generate conditional probabilities that are accurate in some sense. And so you'll see a lot more later on in a later section when you get into training large language models about what those specific measures are. But that's sort of the high level concept. And then there was a question about how do models recognize patterns. I mean, so that's a hugely broad subject, right? There's that's kind of the whole that the whole broad spectrum of the subject of machine learning deals with that. But what we mean specifically in this context is, can I generate a conditional probability function that accurately represents real text, right? In the sense that I just explained. Okay, and then there's another question I see here, which is actually it's a great question, and it gets at the heart of what makes language modeling hard. So probability seems to depend on the context, and so that's correct, right? That's exactly how we're modeling this. How many contexts can be stored in the model for the model prediction purposes, right? So that's exactly what's hard, right? Because you get the sense that, okay, great. So maybe if I'm going to build one of these models, I just have to store, like explicitly store lots of contexts that I've seen in the past and generate probabilities for all of them. But that number of contexts, the number of possible contexts is just going to get astronomically large really quickly, right? I mean, for any reasonable length of context. And so that's, hang on to that question for a minute because we're going to talk about that. But that's, precisely the challenge with building these is that you say, okay, this all seems straightforward enough. Now, how many contexts do I need to store? And you can't explicitly store enough context to do this well. So you have to come up with other tricks. So hang on to that question for a minute. We're going to come to that and talk about that exactly. Um, and then there's also a question about um, do I always choose the next token that has the highest probability? And the answer is no, not necessarily. That's a reasonable approach. But another thing, so I'll give you some examples for other things that you can do. One is I could draw samples from this probability distribution, right? So for example, if I say, okay, I have these probabilities over the next word, pick a random word, but pick a word randomly, with these probabilities. So like with probability 0.031, pick the word office. With probability 0.028, pick the word store. With probability 0.027, pick the word local. And you could do it that way, right? You could sample from this distribution. And if you did it that way, you'd get different sequences every time. So that's one way. That tends to generate really weird results because you end up sampling occasionally, like when you're generating some sentence, you end up sampling, you're going to just sort of get unlucky and sample just a sort of weird word that shouldn't be in that sentence. And then since you're feeding that back into the model to generate more tokens, that's just going to send the whole, send the whole process haywire. So that's not often done exactly in that way. Typically, what's done instead is, you could say, well, let me pick, say, the 10 most probable words, and then I'll sample from among those. Or you could say, you know, sort the words from most probable to least probable, take the set that, cumulatively has probability 0.1 and sample from that set. So that's another way you could do it, right? You can generate samples, but with some constraints to it, ensure that you're actually generating reasonable choices. And then there are even more sophisticated things you can do, like you can say, I know I'm eventually going to use this to generate a sequence. Find the sequence that's going to be the most probable sequence if I chain these probabilities together. So that's getting kind of way ahead of things, but that's a kind of another way you can do it that generates maybe different results than what you get if you just always picked the next most probable tokens. So there are different ways to do this, and you'll see in practice, people generally do it one of those ways. But those are the ones that I described there are kind of the most commonly used methods. Okay, so this idea of generating text is actually really versatile. Um, so let's just kind of give a hint of what I mean by that. Um, so, we saw the example this morning. And we gave this idea of I could generate the next word, say pick the most probable next token, and then I could feed that back into the context and do it again, feed that back into the context, do it again, and keep doing it. And maybe this morning I went to the office as I usually do on weekdays. And that's one way to complete the text, right? But now you say, okay, is that all I can do with it? Is I can, complete incomplete sentences? Is that all language models are good for, is just completing incomplete sentences? And the idea is, you can actually use them for, most language related tasks that you can think of. So for example, what if I fed a model as context this question, colon, what is the largest city in the world, question mark, answer, colon, and said, complete that sequence of tokens. Well, maybe the way to complete that is the next token should be Tokyo and the next token should be period. Okay, well, if my language model can complete um, text contexts like this, it can answer any question I give it, provided that it, accurately generate answers. So basically, if I just feed it inputs that are formatted, formatted in line with the task that I want to perform as a text completion task, I can actually get that model to do really useful things. Like maybe I say, translate the following sentence from English to German, and then I have a sentence in English, and then I write translation colon. Well, if my model's really capable, maybe it'll complete that text passage by giving me the translation in German, right? A really capable model can actually do translation just in the process of doing this kind of text completion. Or what if I want to chat with a language model, right? Maybe I can feed it a context that looks something like this: human colon, how are you? Chatbot colon, and say, okay, language model, go complete that text. Well, maybe the text that it completes is the text that would be an appropriate response for a chatbot. I am well, thanks. And now we've used our language model to build a chatbot that we can interact with, kind of just like what ChatGPT does. And so this idea of generating text is actually, super versatile in terms of, all the different types of language-related tasks that can be performed. And this is one of the reasons why things like ChatGPT suddenly have, kind of become so mind-blowingly powerful, right? Is because finally, um, very capable language models with a lot of knowledge baked into them because the models themselves are large, they've been trained on lots of data, had come along. They had been fine-tuned to understand these chat style contexts. And what you just get out of the box once you have such a capable language model is just something that just works as a very knowledgeable chatbot. Um, so this idea of text generation is a super versatile idea. If you have a language model that can do it well and it can understand sort of these nuances of the prompts that I've given it, like what question colon answer colon mean and what human colon chatbot colon mean, and it can respond appropriately, then you've got a model that can perform a lot of useful tasks for you. Okay, so I want to talk a little bit about, um, somebody had asked this question about how many contexts do I need to remember or how many contexts do I need to learn? And this is relevant in the context of kind of the simplest possible language models you could think of. So there's something called there's a class of language models called n-grams. And the simplest example of that is what's called the bigram model. And so the idea of the bigram model is what it does is it says, okay, if my language model is, basically this probability model that says, give me the probability over the next token given the prior sequence. It says, I'm going to ignore everything. I'm going to ignore all of the context tokens except for the most recent one. It's going to say, okay, yeah, forget about what token 1 to n minus 1 were. I am only going to look at just token n. So in other words, if I was looking at this example and I said, this morning I went to it says, I'm going to ignore everything and just look at I'm just going to look at the last word in the context. And I'm going to try to uh, generate probabilities of what could come next, given just the last word. Well, something like that's actually relatively easy to build, but it's going to be a pretty bad language model, right? It's going to not produce very useful results. And so here's an example of how, kind of illustrating how these bigram models are trained, right? So if I give it a bunch of text, it's basically going to go through and it's going to say, okay, I'm going to look at all pairs of words. And every time I see the one first word, I'm going to keep track of how often each other word comes next. So here I see the word brown. I'm going to say, okay, here's one case where fox came next. And if I keep looking through my text, maybe I see the word brown again, and I see the word cow comes next, and I'm going to record that. And I'm just going to do that for all of these pairs, right? And so if I give you this large corpus of text or this large body of text, I could run through it and I could basically just keep track of for every single word in my vocabulary, right? So let's again say I have 30K words in my vocabulary. So for each of those 30K words, how often do I see each of the 30K words next, right? So you can almost think of like building this 30K by 30K table, where on one axis it's the first word, on the next axis it's the second word, and it just keeps count of how many times it's seen that pair of two. If I had such a thing, I could then estimate that probability. It's just as the frequency with which each next word occurs. So that's this thing that I could build pretty easily from a collection of training text. But and it will give me probabilities, and I can use those probabilities to generate sequences of text. But it's not going to be a very useful language model, right? Because in this example, I would throw away everything except for the word the. And I would say, okay, the last word was the. What do you think the next word is? Well, it could be anything, right? All of this prior context is lost. Or similarly, if I tried to do it in this example down here, I'd throw away all of my context except for the word answer. I would say, okay, the last, or actually, if I was doing tokenization, I'd just keep the colon. The colon has its own token. I would just say, okay, the last token was colon. What do you think comes next? Right? I would completely throw away anything meaningful from the prior context. It is a language model, right? But it's not a very useful one. And so, um, yeah, so how many different entries would I have to keep in my table here, right? So if I'm keeping track of every pair, I'm going to have 30,000 by 30,000, which, it's a large number, but it might be doable to keep track of those. And you could say, okay, fine. Well, the problem was you just looked at the last word. Maybe a better idea would be to look at the last two words or the last three words. Okay, that's fine. But if I want to look at the last two or three words, this table's going to grow now. It's going to grow to 30K to the third if I'm looking at the previous two words in the current word, or it's going to grow to 30K to the fourth if I look at the previous three words in the current word. And this number is getting really, really big really quickly. So this idea, this n-gram, so I call this the bigram with one with two. This n-gram is sort of this generalization of I could keep any n-1 previous words. Right. So the idea here with the n-gram models are training them is simple, right? Like the concept of training them is simple, right? You just keep track of the occurrences of these word pairs or word triples, and you record the frequency. You could generalize that if I wanted to keep track of each sequence of 3 words or 4 words. And for the general n-gram model, I just keep track of the frequency that each word occurs given the previous n-1 words. So it's a simple concept, but it's either going to have too short of a context to be useful, or it's going to require keeping track of so many different contexts that it's not feasible. Right. So the idea here is that suppose you have a vocabulary that consists of V distinct tokens. I've been using 30,000 as my example before. Like that's a typical number for the size of the vocabulary of a language model. So when I build an n-gram model, what we need to specify is for a given token, the probabilities for all possible sequences of V-1 tokens. And so there are V to the n-1 combinations. if I have a context of length n minus one. And then when I'm saying how many probabilities do I need to keep track of, well, for each of those, I need to keep track of v probabilities for each possible next token. So this thing is going to, the number of parameters I need to keep track of is going to scale exponentially in the context size. So it's going to get very, very big very quickly. And it's going to get too big to manage before I have an N that gives me an actual useful, accurate language model. Okay, and here I just want to give an illustration to show this idea that long contexts are necessary, right? We really need long contexts if we want to model language accurately. And we've always already seen this in those few examples that we looked at before, like where I ask a question and have question colon the question and then answer colon. I really kind of would need to go deep back into the context to understand, what is the exact question being asked. But here's a simple example just to illustrate this. So let's suppose I said, my dog is named Joey. Yesterday, Joey and I went for a long walk by the river. The spring weather was beautiful and many people are out enjoying the day. Joey was happy. Happy too. I know this because, okay, so let's suppose that I couldn't model a very long context and I had to limit it to just these words that are in green. So I had to basically chop off everything um, prior to the word many here and just use these green ones as my context. So I had many people were out enjoying the day. Joey was happy too. I know this because, well, maybe a perfectly reasonable thing for your model to say is because he told me so. Many people, Joey was happy. I know this because he told me so. But hold on, Joey's a dog, right? I would have to go deeper back into my context to all the way to the very beginning to see this sentence, my dog is named Joey, right? And so if I want to look at what I should generate next, I should take into account that Joey's a dog. How do I know that my dog was happy? I don't know, maybe because he was wagging his tail or something, right? Maybe it should say, I know this because he was wagging his tail. But that's a very specific detail that, there's really one word that's my clue in my context that Joey being happy, I knew Joey was happy because he was wagging his tail. It's the word dog that's way bit back deep in the context. If I lost that word, right? If I said my blank is named Joey, yesterday Joey and I went on and so on, then he was wagging his tail wouldn't be the right choice, right? I have to know that Joey's a dog, and that's that one specific token um, comes way back in my context. So the fact that Joey's a dog is important. That information in this example is outside the context used. If I want to do this accurately, I need a context that's long enough that I can capture these really long range dependencies in language. And so long contexts are necessary. In order to have useful language models, we need to have these. We know things like n-gram models are really bad at capturing long contexts. Long before I would be able to capture a context of this length, I would have to keep track of so many different combinations that it's infeasible. So that's really one of the kind of key challenges that we're dealing with when we're building language models. So just to sort of give a picture of language models at a super high level, so there have been lots of different approaches that have been used to try to capture these long range dependencies to accurately model language. Like this is the key problem, right? This is the whole problem when you're doing language modeling. So the best performing models that have been introduced to date are generally ones that have been based on deep neural network architectures. So I'm sure you probably heard of deep neural nets. Deep neural networks in various forms have been very good at this language modeling task. And so up until several years ago, sort of the dominant neural network architecture, and again, there will be an entire class of this course devoted to neural networks that will get into a lot more detail on what these different architectures are. Were recurrent neural networks, right? Recurrent neural networks sort of keep track of kind of a hidden state that represents its state of knowledge, and it looks at each item in a sequence and it updates that state of knowledge as it sees new tokens in the sequence. Um, that was the various forms of recurrent neural network were the predominant architecture used for language model up until a few years ago. Um, and training these models is hard. It's difficult to get training right. Um, in order to get them to perform well, you need to use very heavily parameterized models, very large models. And so there was a breakthrough in 2017 where people had been coming up with all these different ways to get recurrent neural networks to work better and better and better. Kind of adding all these different features to them to improve their performance. And one of them is this mechanism, and again, this is something you'll see later, but this mechanism called attention. So attention was this thing that had been added onto recurrent neural networks, and it was shown that when you add this attention, performance improves a bit. And then in 2017, there was this paper that came along that said, this research paper that came along that said, actually, attention is the only part of the model that you really need. You don't even need any of the recurrent stuff. You can throw away all the recurrent stuff if you just use this attention mechanism. Like that attention mechanism itself is powerful enough to model language. And if you throw away all the things that make using recurrent neural networks difficult, you get these models that are easier to train. You can train larger ones than you could with RNNs. And that was really the breakthrough. That was like really the key breakthrough with large language models. And that architecture that kind of does away with the recurrent components and just focuses on attention is this model architecture called the transformer. And so that's really been the dominant architecture used for language models since 2017. And that was really when this whole area just like completely exploded and took off, is when various research teams started going all in on training transformer models and training larger and larger transformer models and seeing like incredible performance emerging from these models as the models got larger and they got trained on more data. So transformers are really, once you really get into the details of, state-of-the-art language models, it's all about transformers, right? That's going to be the place to start. And, I keep saying this, but there'll be another course later on where you'll really dive into the details of transformers. But all the examples that we look at later on in this course are all transformer-based models. Okay, so I want to wrap this section up. So some of the key takeaway ideas here is that language models capture statistical relationships and sequences of tokens, right? That's all they really are. If you kind of want to think about them abstractly, is that you're just given these sequences, and there are important statistical relationships in those, and language models learn how to model those from being exposed to being trained on lots of those sequences. The second one is you can generate text from a language model by conditioning on prior context. So the idea here is that I give some context for the model to complete, and then the model can generate text that completes that context, one token at a time. And it's one token at a time because the models themselves are designed to predict probabilities of the next single token given a context. So here's a context, here's the probability that each word in my vocabulary, right? So each token that I have in my vocabulary is the next token in this sequence. And once you have a model that can do this, then you can use it to generate sequences of arbitrary length by just generating tokens one at a time, plugging them back into the context, and then plugging that new context back into the model. So that all sounds like it's easy. It's not easy because building language models that capture long-range dependencies is challenging. And those long-range dependencies are really critical, right? Being able to know, maybe there's one word way back in the text that gives me all the context that I need in order to generate a meaningful completion. And without the ability to capture that long range context, I might not know that word, right? So that's the whole, in order to get these things to perform well, you got to build models that can capture long range dependencies, and that's the key challenge. And then the transformer model from 2017, that was the real breakthrough where, we were able to start building models that can very accurately model text with very long contexts, thousands of tokens of context. Um, and so that's really where this whole field kind of skyrocketed and became something that's where it is today.